So, welcome back everyone to this NPTEL course on topological phases of matter. We have covered quite a bit. In fact, we have covered most of the fundamental stuff about topological phases of matter, and it turns out symmetry plays an important role in protecting the topological phases as well as classifying the topological phases. So, today we will start the chapter named Symmetry. As I mentioned, that Symmetry chapter is almost decoupled from the fundamentals of topology. So, you can learn it at even earlier or later. So, you can squeeze in this chapter at your convenient time. So, in this chapter we will cover again the fundamentals of symmetry and how the symmetry transformations are done in quantum mechanics and especially in condensed matter. And there will be various types of symmetry that we have to go through. So, at the beginning it may seem like it is a lot of symmetry properties, types of symmetry, but eventually we will narrow it down to a few types, which are going to be discrete, and mainly okay, in the discrete again there will be two types, which will be space time and internal symmetry, and also there will be unitary and anti-unitary. So, we will pretty much talk about 3 to 4 types of symmetry which will belong to these things, and there will be few more which I will also talk about. And then especially in the condensed matter wave functions, we will first demonstrate how these things are applied in first quantizations, especially to demonstrate how things look like in real space and momentum space. The wave functions in these two space. There will be characteristic differences that I want to point out, and then we will spend a lot more time on the second quantizations of all the symmetries and how they are written. And because in second quantizations the Hamiltonian has both the matrix element part and the creation and annihilation operators, which is not the case in first quantizations. So, then the full Hamiltonian versus the matrix element of the Hamiltonian, how they are going to change under the symmetry operations. Then we will take several examples. Some of the examples are already that we discussed in the previous chapters, which were the topological materials, and then we will also take examples which will lead us to the future chapters. And these are the references. This is a modern quantum mechanics book by Sakurai. It has touched upon the symmetries in the elementary way, and then Barnavik's book will be more focused towards the condensed matter, and this RMP, which are also for topological phases of matter. Okay. So, let us start the types of symmetry. So, there are continuous symmetry. Let me even start with that. So, there is so the way we approach this chapter is that we do have a manifold, which is kind of your space time when we define a chart, generally we define a chart in the space and as well as time. So, there will be symmetry in the space time also, the symmetry that corresponds to the rotations, translations, reflection, inversion in space time or manifold symmetry. And when a system, in our case this will be more of a Brillouin zone, when the Brillouin zone has this sort of symmetry, how the Hamiltonian and the wave function transform under those. These are our fibers, okay, and for us the fiber will be psi. Psi usually belongs to some structure group. So, U1, okay, let me write it. Fiber generally belongs to some structure group which itself is a symmetry, right, and based on the structure group you do have the basis states, frame states. So, U1, SU2, SUN, ON, this sort of symmetries are there in the fiber. And these are continuous symmetry that we generally have studied. For example, the wave functions are arbitrary with respect to a phase, so that gives us the U1 symmetry. And then if you have a spin rotations, that gives us the SU2 symmetry, spin for spin half, and for real vectors we have ON symmetries or O3 symmetry in 3 dimensions. So, these are the internal symmetry . Okay. And there will be more. So, now we talked about 2 types of symmetry then. One is space time, another is internal symmetry. So, internal symmetry, by the way, is local within this, within a given base point in your base manifold. So, each wave function is kind of a vertical line, kind of a fiber which belongs to some Hilbert space or a vector space. So, if I just sort of think of the written in terms of some frames basis vector. So, if you rotate them among the basis states, if things do not change, that is kind of the internal symmetry. You interchange the basis at the same base point, and if the theory is invariant, that is the internal symmetry. Whereas, as you go from this point to this point, if everything remains same, then you have a space time symmetry, or if you reflect and so on and so forth. Okay. So, under these 2 types of symmetry, how things would look like is what we are going to see. So, one is space time or manifold symmetry, another is internal symmetry or fiber. So, then we have continuous and discrete, and both applies for both space time and internal symmetry. So, continuous symmetry will be, for example, if I continuously, if I have this manifold somewhere, or if I have a Brillouin zone, or if I have a lattice, if I have a material, if I just shift it from one position to another position, nothing changes. So, that is kind of a continuous symmetry. I can continuously change the positions, or I can continuously rotate an entire sample, nothing changes. So, those are the global continuous symmetry in the space time. And a discrete symmetry would be within the lattice. As you go from one lattice sites to another lattice sites, things remain same. So, that is a discrete rotation. So, you can only discretely by only lattice sites, and then you will also have discrete rotations like C4 symmetry. You rotate by 90 degree in a square lattice, everything remains same. Okay. So, examples would be, for example, continuous translation, rotation, etc. Whereas here it will be discrete translation or periodic translation. So, discrete rotation, and so on. And right now we are talking about space time, but there will be more in this case, such as inversion, reflection. Okay. So, suppose I have some lattice and I have some center of point and I have an atom here, and I wrote the Hamiltonian based on some positions here, positions of atom. Then if I do the inversion to here, and if things remain same, that is the inversion symmetry. And if I put a mirror at this point and then I reflect it to this way, if everything remains same, that is a reflection symmetry. So, these are discrete. You can only change all the coordinates 2 minus and only the x coordinate in this case, whereas y and z remains same. So, these are the discrete symmetries. And the same thing about fiber also, we have this wave function has this phase AC2 and so on. And here internal symmetry, there will be things like sublattice or chiral, then charge conjugation, we will talk in details about this, but sublattice is, for example, we studied graphene lattice. We have two sublattices A and B, and we wrote a Hamiltonian with A and B in the basis state. Then if you change A to B and B to A or minus A, if Hamiltonian remains same, then that is kind of a sublattice symmetry. And chiral symmetry is like a right movers. If I take a wave function which is right movers, let us say right moving plane wave or block wave, then if I rotate to a left moving one, and if everything remains same, that is a chiral symmetry. And in condensed matter we will find that the chiral symmetry is often realized through sublattice. So, they are often taken to be synonymous. And charge conjugations, if I have a electrons with minus charge, then if I change the charge to plus charge, if everything remains same, then it is kind of a charge conjugation symmetry. So, sometimes that is also called particle hole symmetry. And another symmetry that we will have here is, for example, a time translation symmetry in the continuous case, and that will become time reversal. Okay. The arrow of time, if I change going forward in time to going backward in time, if things remain same, then there is a time reversal symmetry, and this turns out to be a very important and unique symmetry, especially for the spin systems that we will talk about. And there is also unitary and anti-unitary. Okay. And which are very much related to linear and anti-linear, and we will discuss that. And proper and improper symmetries. This generally defined for the discrete symmetries. So, if I have a symmetry operator O, if this is plus minus, so if it is plus, then it is proper, if it is minus, it is improper. So, inversion, reflection and time reversal, they are all improper symmetry, whereas rotations, discrete rotations and all are proper symmetry. We will again talk about it, even parity, whereas this is like a discrete rotation like C4 rotation, C2 rotation, and so on. And the final thing is symmetry and something that I will call anti-symmetry. So, this would be if I have a symmetry operator that commutes with Hamiltonian, whereas if I have a symmetry operator that anti-commutes with the Hamiltonian, we will call it anti-symmetry. So, in literature one would, they also call it anti-symmetry, as they also call it symmetry, but it is sort of much easier to call it anti-symmetry. So, I will try to stick to this nomenclature called anti-symmetry when confusion may arise. Just to emphasize that symmetry operator anti-commutes with the Hamiltonian. So, here most of this symmetry, time reversal, inversion, so on, whereas the chiral, charge conjugation, are the examples of anti-symmetry, and we will see the consequence of those. Okay. So, unitary, the definitions, let me just start with the definition of symmetry. And then we will talk about unitary and anti-unitary. Okay. So, again we will do it briefly. I am assuming that symmetry and group is something that you already know. So, we will do it briefly. So, we will say that if I have a, so let us start with some Hamiltonian in some first quantized Hamiltonian written with some energy. Okay. So, let us say I change psi to psi prime, which is related to psi with some operator, transform with some operator, and so the dual space will also change. So, under a symmetry operator, what are supposed to remain preserved and what are allowed to change. So, state is allowed to change, state and operators change. The length of any vector, a state, which is the inner product, expectation value, those are the physical properties which should not depend on the symmetry operator if there is a symmetry by definition. Properties in general such as expectation values. Right. So, if we insist that the inner product should remain invariant, so from the left hand side it is obvious that this has to be identity. So, O must be unitary. Okay. Now, for the expectation value with respect to some operator A, so you can see that I put a hat for O, but not for H, because H is often taken to be Hamiltonian as an operator in quantum mechanics. So, there should not be any confusion, but sometimes some operator is not clear whether this is an operator or number. So, I will try to use a hat if there is a confusion, but for the time being I do not see that there should be any confusion. So, we will not be careful about putting a hat. So, starting from here, so we will get psi O dagger A A prime, and then from here so now this should be equal to this. So, A should transform as, okay, and let us remove this. Which is to say A prime is related to right, by just putting O from this side and O dagger from this side, and by putting the fact that O is unitary, you will get this equation. Okay. So, state change like this and operator change like this. under which the physical properties remain same. Okay. And now, if I have a operator that commutes with the Hamiltonian, rather I am interested in the, so what we will do now is that such unitary operator will denote by u. Okay. So, if this transformation operator commutes with H, then U is a symmetry, right. So, U and H has the same eigenstates, right. And starting with the right, starting with the Heisenberg equation of motion, if U commutes with Hamiltonian, so U is a concept quantity. Now comes the interesting one, the anti-unitary and anti-linear operator. So, there are 2-3 proofs that we may have to do, and some of them I can leave it for you to do as a homework. Let us start with the definition. So, it was first proposed by Wigner in 1931. So, one thing he realized that excuse me, one thing he realized that it is not the inner product itself gives you the full length, right. It is the absolute value of this, or the length of the vector is the square, you take the square of this inner product and then you take the square root, that is supposed to remain invariant, right. Not necessarily each one, it may actually have even a complex space. So, which means if I expand it, and let me even make it general, psi 1 2 psi 1 2. So, that is the definition of this. Okay. So, now if it is unitary, we take this to be equal to this for unitary, right. we can realize we can even generalize this. It's a strong condition. How about we generalize this, that what if this one is equal to this and correspondingly this one then will be equal to this. So, the star part is equal to this, and that we will call it anti-unitary. So, we will denote anti-unitary operator by A. Okay. So, psi 1 prime is related to psi 1 by A, and the same for psi 2 prime. Star this is still identity, yes, identity. Much like the unitary operator, but once you put that, you get psi 1 and psi 2. So, it turns out, and we can show it explicitly, but let me just state it. Anti-unitary operators are antilinear, not necessarily the other way around. So, what is an antilinear operator? A is antilinear if A acting on a state expanded in terms of the basis with A and B being complex number. Generally, for a linear operator, any scalar number, it just passes through, but that is not the case for antilinear, just by definition. So, what we will get is it will still pass through, but give a complex conjugation, and then it will act on the basis states. For antilinear, if it was linear, you would have gotten for linear operator. So, which means there is a complex conjugation operation that is inbuilt in the anti-unitary operator, is inbuilt in anti-unitary operator, which means we can always split an anti-unitary operator as a unitary operator and complex conjugation. So, complex conjugations is exactly what we just defined. This is like a complex conjugation. So, what it does is that wherever it finds a complex number, it gives you a complex conjugate of that variable. Okay. So obviously if you apply it twice, you get back the same, whereas this one u dagger u is equal to identity, and here also a dagger a equal to identity. A square equal to plus minus 1, whereas for, and we are going to talk about only discrete symmetry. So from now onwards, if you do not say discrete symmetry, it is almost implied. If it is not implied, I will rather explicitly mention, but if it is not explicitly mentioned, then you always assume that we are going to now talk about only discrete symmetries. So as for discrete unitary symmetry, u square is identity. Why? Because I apply and I get psi prime. So it is like a let us take the example of inversion. So I inverted all the positions x to minus x, y to minus y, and z to minus z. So if I apply twice, in which all the positions are inverted, so if I then again apply, I again invert it back. So I am supposed to get back this. So that gives us u square equal to identity. But in this case, you can get a phase of two pi, which is same as 1, or you can get a phase of pi for minus 1 case. And that is sort of intuitive because it does change the phase, right? It's complex conjugate. So let us prove this. So a square equal to u k u k. So this one, and k is equal to k inverse, just a complex conjugation, right, and k square equal to identity. So this is then nothing but u star and then u. And because it does not change the length, so let us just assume that this is some phi times identity, and we want to figure out what is phi, right? Because I mean we always want the inner product to be invariant. So in this transformation also we see that it only changes by a phase, so it does not change the length, because if it has to change the length, then we have to be very cautious and it won't even happen, because you can see that this is the length. So if I get some length, then it has to be the inverse of length, and you will see that such a transformation is not possible. So it can only change things by a phase. So that is why we just took it to be just a phase times identity. So u u star equal to e to the power I phi identity. So let us multiply some u dagger to u dagger from left from both sides. This is equal to identity since u dagger equal to identity, it's unitary. Okay, you take a complex conjugative with transpose of this entire thing, then you will see that you will get this equation, and that is identity. So transpose of an identity is identity. So this is one is, so that means we get u is equal to e to the power I phi u. This is equal to, let's apply it again. So u transpose is e to the power I phi u transpose. So that is e to the power 2 I phi equal times u. So u is equal to e to the power 2 I phi times u, which means this is 1. So e to the power I 2 phi equal to 1. Which implies e to the power I phi can be plus minus 1. Okay. So now two things happens. A square equal to plus 1 is equal to minus 1. Okay. So this leads to Krammer's degeneracy of state and its symmetry transpose states are degenerate, whereas this leads to A and okay, let me if A state is also an eigenstate of state, if H, because they commute, right? If, or this entire thing is when they commute, when H A commute. So for unitary symmetry we always say that if two operators commute, they share the same eigenstate, right, and that is exactly the statement here, and this proof is very trivial, you have done it. But if A commutes with H, this is however not an eigenstate of A if A square equal to minus 1, rather they are orthogonal. Okay. So this is called Krammer's degeneracy. So we will prove it either in first quantizations or in second quantizations. Okay. So with that we will stop here today, and we will start with the other symmetries, inversions and all in details. Thank you very much for your attention, and see you in next class.